So, welcome back. We will continue discussion with the solution of the heat equation we started in the previous lecture, and now we complete the formula. So, we are in the process of analyzing this integral. Okay, so, again let me write it. So, we had obtained the solution in this form. G y e to the minus a square lambda square t cosine of lambda y minus x d lambda then dy. So, we analyze this thing separately and we obtained this function h theta, and there is a 1 by a root t, and again we substitute back this variable eta in the original variables. So, that simplifies into, so let me write it, 1 by 4 pi a square t to the minus half minus infinity to infinity exponential. So, since expression is little big, so let me write exponential. So, y minus x square divided by 4 a square t into g y dy. And you recognize this multiplied by this is precisely the fundamental solution of the heat equation. So, this is just write it here, k of x minus y t g y dy. So, k is the fundamental solution of the heat operator. Which we first obtained as a special solution to the heat equation, and now it also makes appearance in the formula we are trying to derive for the heat equation. Okay, so, just let me write u x t. So, we also see that k is, apart from the properties I listed earlier, k is also symmetric. Meaning k of x t is equal to k of minus x t, t positive. Okay, so, if t is positive, so that you can, because in the exponential term this sits as an x square. So, x and x square equal to minus x square. So, that is, there is no change there. Okay. And now we look at just a few comments on this formula. So, let me just introduce some notations. So, if f and g are functions from R to R or R to C, okay, their convolution is defined by convolution is defined by. So, convolution of two functions is again a function. So, defined by f star g of x minus infinity to infinity f of x minus y g of y dy, which we also can be written as by changing the variable. So, this is f of y g of x minus y dy. So, this g star f. So, provided the integral is finite and other so, this f, the star operation, the convolution operator is a commutative operator. So, in this sense we can write with this notation u x t as k star. So, I will put a function here t star g of x. So, the u we obtain by heuristic arguments can be written as convolution of the fundamental solution and g. That is what I want to comment. Okay. I want to stress that. So, now, we obtained this formula by assuming several steps in between, but the final formula is very neat and it makes sense for example, if G is bounded, because of the exponential factor in k, u is well defined. So, there is no problem at all. So, the integral exists for all t positive. Okay. And now, we try to show that u is indeed a solution of the heat equation. We cannot claim uniqueness. So, we just say, so let me state this as a theorem. So, if G is continuous and bounded, we have to assume continuity does not imply boundedness because we are on the real line, that is not a compact set, and bounded. Continuity is also not required if we are using Lebesgue integral, but let me just state that G is continuous and bounded, then so let me put this as 2, then u given by 2 indeed satisfies the heat equation T positive. U also satisfies the initial condition in the sense that so limit u of x t as x tends to eta and t tends to 0 is equal to g of eta. So, eta is a real variable. Okay. So, in general this limit is satisfied at all the points of continuity of G. So, if you are not assuming G is continuous everywhere, so this limit exists wherever G is continuous. Okay. So, the proof of this theorem depends on one more important property of the fundamental solution. Okay. So, let me just so proof. Okay. So, recall the again properties of the fundamental solution. K is a C infinity function for x in R and T positive. K is symmetric, we saw that. And K satisfies the heat equation. So, this is we also saw this K x x for x in R and T positive. So, one more important property, I write it here. So, if you integrate K x minus y t with respect to y, not on the whole real line, but you just leave stay away from this x at a positive distance, and then you take this limit as t tends to 0, this is 0 uniformly in x, that is important, uniformly in x. So, the usual epsilon delta, if you take that definition of the uniformity, means that delta does not depend on x. So, this is crucial in verifying this part of the theorem, this part. Okay. So, we will come to that. Okay. Just so, proof of 3, that is not very difficult. Okay. So, again let us write that what is in terms of K. So, you consider this x minus y bigger than or equal to delta, delta is positive, delta positive fixed. So, for any delta positive, so if you stay away from the x and then this limit is 0. So, make the substitution x minus y by 2a root t is equal to z, and then this integral is changed to 2 by root pi delta to infinity. So, there is a portion coming from minus infinity to minus delta and delta to infinity, but because of symmetry we can convert that minus infinity to minus delta integral to delta to infinity integral, and that is why that 2 comes. So, it is a very simple one, there is no complication at all. Okay. And okay, sorry, the delta. So, this becomes delta by 2a root t, because we are making this substitution. So, if x minus y is in absolute value bigger than delta, then mod z is bigger than or equal to delta by 2a t, 2a square root of t. So, what you do here is now the simple thing 2 by pi. Now, let me write that you add a z and divide by z e to the minus z square, and this we can do because z is away from the origin, and for 1 by z you replace it by z is bigger than or equal to del divided by delta divided by 2a root t. So, 1 by z is less than or equal to 1 by root pi 2a root t by delta, and the remaining integral you can just write it as 0 to infinity. Now, there is no problem, 2z e to the minus z square dz, and this integral is just 1, and since root t sits in the numerator, so that goes to 0 as t goes to 0. Of course, we are always considering t positive. So, let me stress that also there is a square root there. So, that is this proves property 3. So, now it is very easy to prove the stated theorem. Okay. So, again differentiating under the integral sign. So, this is let me make a comment here, differentiating under the integral sign. So, we obtain u sub t is same as minus infinity to infinity k sub t x minus y t g y dy, and u x x is kxx x minus y t gy dy. So, the justification of taking the differentiation under the integral sign, the important thing we use here for the exponential function. So, if b is positive, so this is a small result in analysis, then for every n positive, can be integer, it can be anything, we have x to the n e to the minus bx square is less than or equal to some constant which depends on n e to the minus b by 2 x square for all x positive. So, this crucial property helps us in taking the differentiation under the integral sign, and that immediately implies, because the fundamental solution satisfies the heat equation Ux. So, the hard part is proving the initial condition. Initial condition is also satisfied. Okay. So, before doing that thing, since k is a C infinity function for t positive, and just like we did it here, taking the differentiation under the integral sign, it follows that u dot t is also a function as a function of x for t positive. So, though initially at t equal to 0, g may be just a bounded function, but this heat kernel makes the solution a C infinity function for any t positive, and this is referred to as smoothing effect, smoothing property. Okay. Smoothing. Okay. Now, we will come to the verification of initial condition. Okay. So, let G be continuous at eta. Then given, so this is just definition of the continuity, epsilon positive, there exists delta positive such that g of y minus g of eta is less than epsilon if y minus eta is less than 2 delta. 2 delta for technical regions, otherwise simply write delta there. Then consider u of x t minus g of eta. So, let us simplify this. So, I forgot to mention one more property which I am writing now, k x minus y t dt t dy, sorry, minus g eta. So, here is, so this is for t positive. Here is the property. So, this minus infinity to infinity k of x minus y t dt. This is an easy verification. This is simply 1. Okay. And you just go back and see the expression for k. You, this is, sorry, making mistakes. So, this is for all x and t positive. Okay. So, there is x here. So, this is just constant 1. Okay. So, verify this. So, this is another property of another important property. So, this we can combine the two integrals and write it as x minus y t. So, g y minus g eta. Eta is fixed. Okay. So, eta is fixed there. And now you break the integral into two parts. So, this mod x minus y bigger than or equal to delta and mod x minus y less than delta. So, delta is coming from here. So, the same delta we take, we break this integral into two parts. So, now we can rewrite. So, let me just again write it. So, u x t minus g eta absolute value, now we take absolute value here, less than or equal to mod x minus y less than delta k x minus k is a positive function. So, that is also k is a positive function because it is exponential. So, g of y minus g eta dy plus x minus y bigger than or equal to delta k of x minus y t g of y minus g of eta dy. Okay. Now, concentrate on the first integral. Okay. So, here x minus y is less than delta. So, what about y minus eta? So, y minus eta by triangle inequality is y minus x plus x minus eta. So, if I also take x within delta neighborhood of eta, so this is less than delta, another delta, so that will be 2 delta. If x minus eta is less than delta, and that is anyhow we are going to take the limit as x tending to eta. So, this assumption is fine. So, that makes y minus eta less than 2 delta, and by the assumed continuity property g of y minus g of eta is less than epsilon. So, the first integral, okay, so it's just this is separate thing. So, this is less than epsilon because the integral of k is 1. Okay. So, the first integral. The second one, so we are assuming g is bounded. So, this is less than or equal to say 2 m because g is bounded. So, m is the bound on g. So, this is 2 m and x minus y bigger than or equal to delta k x minus y t dy. And the third property of the fundamental solution, since delta is positive, say that this goes to 0 as t goes to 0. So, we can make it less than 2 epsilon if x minus eta is less than delta and t sufficiently small. And that proves the required. So, finally, what we have shown that absolute value of u x t minus g eta is less than 2 epsilon if x minus eta is less than delta and t is sufficiently small, and this completes the proof. So, though we started with some heuristic arguments, we have arrived at a formula for a function u, and which we are able to show that it is a solution of the heat equation and also satisfying the initial condition as described in the theorem. Okay. So, with this we will stop here, and in the next lecture we continue from here and discuss uniqueness and some other results. Okay. So, just remember this, and this is referred to as Fourier Poisson formula. Okay. So, I conclude here this talk with. So, though we started with some heuristic arguments, but we arrived at this Fourier Poisson formula, and under boundedness and continuity assumption on G, we did verify that it satisfies the heat equation and the initial condition. And in the next lecture, we will discuss uniqueness and non-uniqueness results, and also heat equation in a finite rod. Thank you.